Hello, my mathematical friends. Today we will do a meditation about arctangent. And specifically, we're going to look at this function here. F of u is arctan u plus arctan 1 over u. Very interesting function. And it reveals interesting things about arctangent. So we want to study it over all of R and see what happens. If anything interesting happens in various places in the real numbers. Well, the first thing we can notice is that f of u is not defined for u equals 0 because of this here. So that's interesting. And this will become evident when we graph it and look at it more carefully. So in the next part, I want to look at arctangent a little more carefully using some figures. Right, okay, now I have some figures to help me here. Let's ignore this little line for a moment, and here, the little line here. I'll tell you what that's about in a minute. So with this figure, here's my x-axis. This is positive direction for y, so u is positive here. I can now figure out some things. So tangent of theta, this is u over 1, okay, and therefore if tangent of theta is positive, u is positive, theta has to be positive also. So theta positive because u is positive. Very good. So arctan of u is then theta, and this is positive. Now, let's make u small. So I'm going to take this point here and reduce it down in size until it comes down to here. And I'll get a small u here, and that's what this blue line here is about. So now my theta also becomes small. So it's pretty obvious from this diagram. As u goes to 0, theta goes to 0. And so that means as u goes to 0, arctan u goes to 0. Okay, very good. So we figured out some behavior of arctan in the first quadrant. So now let's look at the fourth quadrant here. Now this is a bit different. Here's my x-axis. This is negative y direction. So my u here is smaller than 0. It's less than 0. So let's figure this out. So what's tan of alpha? That's equal to u over 1 again, but now u is less than 0. Okay, so arctan u is equal to alpha, and alpha is less than 0 because tan is less than 0. This means alpha is less than 0. I think that's how the convention goes. So, okay, and now we'll reduce u, take this point, bring it up until it becomes small u here. Now alpha is small, so u goes to 0, approaches 0 from the negative direction. Well, alpha will approach 0. That means as u approaches 0, arctan u also approaches 0. Okay, that's very good. It has very sane behavior, arctan. But the other one, arctan 1 over u, it's a little bit less sane. So let me get some figures together here. So here, let me try something very similar. So I'll calculate tangent. This is in the first quadrant. So here's x-axis. This is positive direction. So tangent of tangent of theta is 1 over x, the way it's set up here. And x is positive. So because x is positive, theta's got to be positive. Okay, so arctan 1 over x is theta, and this is positive. So what about if we make x small now? So x goes to 0. Now, this is what I'm doing here. I take this point, I shrink it down all the way down, I make x very small. What happens to theta? Well, theta gradually approaches 90 degrees. So theta approaches 90 degrees, pi over 2. And so I can say that as x goes to 0, arctan 1 over x approaches pi over 2. And notice it's plus pi over 2. It's positive pi over 2. So let's try to repeat the same calculation, but in the fourth quadrant. So this is my x-axis. This direction is negative now. So this is a -1 here. Okay, so let's see. Tan alpha is -1 over x. Okay, but x is positive. That means alpha is negative. Because if x is positive, then -1 over x is negative. All right, so arctan -1 over x is equal to alpha. Very good. And so what happens when I bring x to 0? So x actually is positive. Keep that in mind. Well, okay, as x goes to 0, this shrinks down from here all the way down to here. X is small. Now alpha is going to be near minus pi over 2, minus 90 degrees. And so what we see is that as x goes to 0, arctan 1 over minus x, I'll put the minus from the top to the bottom, it makes no difference. This goes to minus pi over 2. And if I substitute for this, instead of I call minus x, I call it u. So let's say u is minus x. Then for u less than 0, okay, I have to change from x positive to u negative. Then I have the following. I'm missing an n there. Arctan 1 over u goes to minus pi over 2. All right, so that's a bit of careful thought involved there, but it's very interesting. Okay, so when I approach 0 this way, I get pi over 2. When I approach 0 the other way, I get pi over 2. So that's a huge problem. That means our function is not continuous. So f of x not continuous. But actually, it's more than that. The problem is bigger than that, because f of x at this point, okay, so not continuous at x is 0, that kind of maybe is kind of understating it a bit. The real problem is f of x is undefined at x equals 0. It's not that it's not continuous. Like I will show you in a moment, for a step function, yeah, it's not continuous at the step, but it's still defined. But here, I mean, it's not continuous and is not defined, because 1 over x is not defined at 0. So this helps us visualize in our mind, like this and this. Like you can close your eyes and you can sort of see how this function tan 1 over u behaves in the negative region and in the positive region for u. And we'll plot a graph of that to check our intuition. So here I've got a plot of arctan u, and that's in red here, red. And I've got arctan 1 over u in blue here. Okay, so that's arctan 1 over u. So this is an amazing graph. I mean, I love looking at this, the way it intersects each other. Like, it's really cool. And you see that there has to be some magic involved here. And there is, you'll see in a minute. But what's very interesting here is, let's consider these points here and here. You may think, well, maybe this is like a step function. So I have a step function like this. Let's say it's from -1, and then there's a step and it goes to +1. Well, it's not the same thing. I'll show you. So let's say g of x is 1 when x is greater than or equal to 0, and here g of x is -1 when x is less than 0. This is my step function. Step function. It's not the same, and it's interesting to contemplate why it's not the same. Well, because at this point here, 0, x equals 0, g of 0 is defined. G of 0 is 1. Okay, it's not continuous because there's this step, but it's defined here. G of 0 is 1. But here, no, this blue is not defined at x equals 0. Not at all, you see. The x equals 0 is outside the domain of definition for this. So the domain for arctan is good. It's all of R. But the domain of arctan 1 over u is got to be R minus the 0 point, because you can't have 1 over 0. It's not allowed. It's undefined. And even if it was defined, the limits from the left and right are different, so it's not continuous at that point. So that's very interesting. Indeed, it's very interesting, but we want to prove something about this function here, arctan u plus arctan 1 over u. This should be u equals 0. And okay, so we will start to do that in the next part. Let's investigate f of u a little further. Now I'm wondering if I wrote x for u in part 3. Let's scroll up and have a look. Yeah, I did. Yeah. It's so easy to write f of x. We're so used to writing f of x. Okay, let's investigate this a little bit. So this is the u-axis. Let's take points along the u-axis and add the heights of these curves. So if I take a point here, u is 0, the height of the red curve is 0, and I add the height of the blue, and I get a point on the line y is pi over 2. Likewise here, if I add this height of the red, the height of the blue is the same, I get the point here. Here the height of the blue is low plus the height of the red, which compensates. It gets higher by magic. I get another point. So it seems that all these points, when you add them, I'm always going to get a constant pi over 2. And likewise here, you can do the same kind of study here. The points should be on the line minus pi over 2. That's very interesting. So we can conjecture this. Pi over 2 when u greater than 0 and minus pi over 2 when u less than 0. Okay, how can we prove this? Well, I'm going to prove it for the positive part of the real line. We'll take a triangle, a right angle triangle with 1 and u sides, theta and phi. And let's look at tangent theta. Tan theta is u over 1, and that's u. So arctan u is theta, and tangent phi, that's opposite over adjacent, that's 1 over u. So arctan 1 over u is phi. And so let's add them together, like in the f of u formula. Arctan u plus arctan 1 over u is theta plus phi, but theta and phi, they're angles in a right angle triangle here, so they must add up to pi over 2. Now that's really, really beautiful, so we've proved this part, very beautiful. And as an exercise for you, you prove it for the regime when u is less than 0. I set up the analogous argument. Now these properties here that I've used, they are really magical properties of arctan and tan. Very beautiful to see this. But you know what else is beautiful? calculus is beautiful, and that has a lot of beautiful stuff in it. And in the last part, I will show you a calculus proof of this, and it's going to be magical. Let's start by finding some derivatives. D by du of arctan u, well, that's 1 over 1 plus u squared. And du of arctan 1 over u, well, I have to use the chain rule for this, and I'm sure you know how to use the chain rule, so I get something like this times, now the derivative of the inside, that's 1 over minus 1 over u squared. But this is quite interesting. When I multiply this, look what happens. This and this, they give me 1, but this and this gives me u squared. So it's kind of really freaky how this works out. Okay, so our function is, if you remember, arctan. Well, we got to remember because we've written it down like so many times. We have to remember. Okay, so this is our function, and we want to now find the derivative of this thing. Okay, so that's 1 over 1 plus u squared minus 1 over u squared plus 1, and that's 0. So lo and behold, derivative is 0 everywhere. And by everywhere, what do I mean? Well, I mean on this domain, and you know, u is not 0 because it's not defined, and it's not continuous. Like if it's not continuous, you can't have a derivative at that point, but it's not even defined at that point. So okay, so very good. And now we can conclude with some interesting computations. Let's write our domain of definition like this: 0, and it's not inclusive, so it's kind of a open set bracket here, and same here, it does not include the point 0, and this is positive infinity. So okay, so we have two separate behaviors here. In this part, f of u is 0, and this means that f of u is a constant. F of u is a constant. Okay, so let's calculate what that constant is. Well, we take any member of this interval. I'll take -1, and let's compute this. F of -1 is, well, we get that, but it's easy to compute arctan of -1, so that's minus pi over 4, and this is plus minus pi over 4 like this, and this is minus pi over 2. But since f is constant, f of u must be minus pi over 2. I found it for one value, but that's good enough. All of them will have the same value because f is constant. That's the beauty of this calculus argument. Think about it. And now on the other portion of the domain of definition, f prime u is also 0, and that means f of u is a constant. And just because f prime is 0 doesn't mean everything has to be the same constant. It doesn't have to be the same. It's a constant. It doesn't have to be the same constant on this part, on this domain, part of the domain here, and on this part of the domain here, because we have a discontinuity. We have discontinuity, and so it's not the same constant. That's kind of really interesting to think about. Okay, so let's take a point in here. 1 is good enough. Let's compute f of 1. Everything in this part of the domain, in this interval, the f of anything in this interval is going to be the same for all of the points in this interval. So I just choose one of them, and I get that, and that's pi over 4 plus pi over 4, and that's pi over 2. Very nice. It works. So f of u is all the same for any value of u in that interval. Okay, and that's beautiful. And now I can actually draw f of u. so I can sketch it. And this is what it looks like. This is my sketch of the function f of u. And notice it looks like a step function, but again, I want to stress it's not a step function really, because it's not defined at this point here. U is 0. There's no f of 0. So it's an open set here and open set here. That's very interesting to think about. And here constant, and here constant. And I would like you to think about this argument that we used here. It's a very beautiful argument. I think it's just as beautiful as the geometry argument, but it's a different type of argument. But it's very useful. I've seen it used in many other places. Well, that's it for today. I hope you liked this. If you like the magic of arctangent, then click like and subscribe. If you liked all this analysis combined with geometry, well, click like and subscribe. And I will see you next time.